close to a neighbor, you might need to get up and talk with a neighbor. And just pick any category and any question, whatever it is you want to say. These are to sort of guide you. I'm going to point out some questions I think are interesting, particularly interesting. And like, for example, what is our operative definition of galaxy in this regime? So dwarf and satellite galaxies. Do we need to revisit this? Does it matter? There's an interesting question. And let's see, there's a lot of interesting questions here under the Milky Way galaxy, including, is the picture of disk formation from the Milky Way consistent with high-Z observations? Worth thinking about. And in metallicities, there's all sorts of questions, but you know, what information can we really extract from metallicities, including enrichment history, spatial variations, etc. I think I would add, what do we trust? And okay, so find a neighbor, have a chat. What's your burning question from this list? And have a discussion about it, and then we're going to be asking you your thoughts. You got 4 minutes, go.
This is not planned to continue the session now. We were supposed to have a lunch break and end. So we ran so late this morning that people brought in their lunches and then so
that's fine.
everything okay with you?
Yeah.
Okay. Oh, thanks for changing the batteries.
Yeah.
So it turns out that our Zoom recordings are just ready down there. So we have a backup for the. Do you have any problems today? So
Okay, who's ready to start the discussion? We can see lots of groups have had some good discussions, and there's been some waving of hands. So, who would like to start?
Should we ask, did anyone
talk about measuring metallicities in gas and stars?
Anyone? I see, okay.
We talked about it because we would love to have it. We don't know the answers to a lot of our questions. For example, there's a question about abundances in gas and young stars. Maybe someone could tell us. I asked Pablo here, what are good ways to get the metallicities of young stars, right? I mean, it's one thing to study things that Sandy studied with all kind of calciums and irons, but can somebody guide us on, I mean, we do see a lot of young stars. So.
Yeah, Andrew actually just asked me that exact same question. So Fabio Breslin and Rolf Gudritsky's have been doing work on this. They've been doing red and blue supergiants, and so they've been measuring metallicities of those. And I would say it's not, it's difficult to measure abundances in these stars and using the absorption lines, but overall the metallicities lie, somewhere in the middle of all the disagreements, for whatever that's worth. Yeah, but they're looking at that across entire galaxies, spiral galaxies, where they've also been measuring H2 region abundances.
So Roman and I was talking about how he brought up that we were kind of curious how the outflow from either stars or AGNs can affect the metallicity gradient, and that was inspired by Andrew's talk, showing that the metallicity gradient can be changed by inside out and upside down evolution of the galaxies. But then we found one thing we were not clear is that if you have some outflow from the either stars or AGN after the upside down already kind of approaching the end, then how does that change your metallicity gradients in those galaxies if those processes are taken into account?
Yeah, I can just respond by saying there's no question, at least in the simulations, I think there's plenty of observation evidence for metal-rich outflows. So metals are being lost. The key question is, are they being lost in a radially dependent way that would further modulate this? And we should look at this in the simulations we have it. I don't know if there's any attempt to try to do this observation. It sounds tricky, but maybe there is some work.
Well, in big data sets like SEMI and MANGA, what you do see in some galaxies, and particularly the more evolved star-forming galaxies, you do see a drop in the metallicity in the center sometimes. Just goes right down. And I've always wondered whether that's due to outflows, but I'd love to hear from some theorists.
But that would be an instantaneous kind of measurement. But I think if you ask a question, Andrew, like in the center, and if I can look at for the amount of stars that have formed there, what fraction of the metals generated have been removed? I mean, my gut feeling would be that you would expect to find that in the center it's large, and in the outskirts, where the disk just settled down yesterday, the stars started forming there, and feedback is not going to be effective there anymore, because now you live in a very massive halo, whereas the center formed when the host halo was much more lower mass. And that sort of is consistent with a lot of work that people have done on angular momentum and trying to understand why the disks have the shapes they have. And the argument be that the low angular momentum material that forms early on, you need to blow a lot of it out and not in the outskirts. So I would love to see how that looks like in the simulations, whether the simulations actually do that.
Yeah, I mean, my base intuition is when the outflows are strongest at early times is also when you get the most metal mixing. So that may not be as relevant. I think probably the more interesting regime for this question is when you start to have a disk, so that there isn't quite complete radial mixing. But it's an excellent point. We can look at.
Okay, who discussed the Milky Way and disk galaxy formation evolution topic? Nobody? Nobody that wants to share their thoughts. There must be people that discuss Milky Way and disk galaxy formation evolution. Okay, dwarf and satellite.
Oh.
Yes? I don't see him here.
Does anyone want to opine on high redshift disks, and does there exist tension? Certainly been a lot of papers on this.
Yeah, so I think there's strong evidence that disks exist at high redshift in JWST observations. They're not terribly common. The fraction falls off with redshift, but you can get 30% of disky-like objects at redshift 3 and a smaller. Those are the numbers that Mark Huerta's company showed us, I think yesterday, from his analysis of. But so is that a problem for fire?
Well, so that's why I added this question, which is the mass dependence, because I think you cannot at all talk about redshift dependence of diskiness without simultaneously talking about mass dependence. And if anything, I think the mass dependence is probably stronger than the redshift dependence. That's my own intuition. So, I mean, I can tell you, like when you look at one of our Milky Way simulation movies, these things at redshift 3 are not what, by and large, people are measuring, right? So I think if, we have some massive, we have a handful of more massive simulations that we're in the process of analyzing, and I think that will look very interesting. But I think most of our simulations, which are Milky Way mass below, just aren't the regimes where people are actually doing these measurements at high Z. So it's harder to make that comparison. But maybe Ben wants to.
So this is not what we talked about, but it's related to things that were just discussed, which is that at sort of intermediate redshifts, it's possible to measure outflows and see that they're preferentially aligned with the minor axis of presumably disky galaxies. So this measurement can be made at redshift 1-ish. It would be interesting to know whether this is something that is occurring at higher redshifts. Because that would probably have some bearing on both the effect of outflows on the galaxy and the question of whether outflows are escaping the galaxy or how far they're getting into the CGM. But, I don't know if that's observationally accessible or if maybe it's just like a sample size question. I think that, there's a fairly solid detection of this effect at redshift of 1-ish by like the work of Rungman, Bordelais, and people like that. I think at higher redshift it's much less certain.
I was just going to add that, on this point, something that we've talked about for years with all these comparisons with fire. I mean, there's limitations on the simulation side, not just physics, but also sample size to make these comparisons. But I think, it's really important, if we want to assess this quantitatively, that we agree on sample selection and definitions of what diskiness even means, right? Are we talking about stellar disks or gas disks? And what's the definition of diskiness? Is it a kinematic definition? And it's not the theorist's J over J circ definition, because that's not measurable observationally. Is it a V over sigma at this radius, at this resolution? Because this does make a difference. And, to Ben's point, I think, it's worth reminding people that even at Z of 0, we don't have a good observational understanding of the disk fraction at low masses of dwarf galaxies, right? There aren't uniformly selected, say, stellar mass selected samples of small dwarfs that we have all of them followed up for, say, gaseous disks. If you look at the 21 centimeter samples that are famous, samples like Spark or Little Things or things like that, those are largely selected to be H1 rich, very extended. Those are your best case possible scenarios for finding a disk, right? So there's certainly progress on this, and we've heard about some of it, but I think this is something we need to be, now that we've moved into quantitatively, not just qualitatively, can we form a disk? Are we forming the right number of disks at the right places and the right times? I think we really need to be more quantitative about those definitions.
Sandy and then Frank.
I'd just like to ask a kind of a basic ignorant question. It's just occurred to me recently because the density fluctuation spectrum of dark matter, if viewed from the lens of delta M over M, is curved. It changes slope as we go to smaller masses and earlier times. And I just wonder if anybody has looked at the lambda structure of very early forming small dark matter halos, and is it any different? Is it larger or smaller than, in general, than the halos? Yeah, the lambda of very halos. Yeah, the spin parameter. Has anybody looked at that?
I know that people have looked at it, but I can't remember.
Yeah, so it's smaller. So I was looking for my paper, but it's not that small. It's of the same order, but it's systematically lower at higher redshifts. Why? Well, I guess that all the structures haven't developed at all, and there are not too many torques. I don't know.
So to follow up on comment that Phil made, that we're now in a stage where we're making really beautiful looking disk galaxies. I have a question for the people that looked at these simulations in terms of how well are we doing in fitting the Tully-Fisher relation. There was one observational fact about the Tully-Fisher relation is that the scatter in the Tully-Fisher relation is not correlated with size. It's opposite to the Faber-Jackson relation, where if you plot luminosity versus velocity dispersion, you have a third parameter, which is the size, and disks don't do that. And many years ago, with Aaron Dutton, we wrote a paper arguing this is actually really tricky to get right, because especially if you take adiabatic contraction into account, the natural tendency is if you adiabatically contract, then basically your velocity goes up because you're more concentrated and you get smaller. And so you naturally start introducing these sort of correlations. It's quite natural. So, I think you or some of the people here showed today that in the simulations there's actually, you see adiabatic contraction in these simulations. So do they now therefore introduce a correlation at the fixed luminosity between Tully-Fisher scatter and size? Has anyone ever looked at that? No, it's consistent with the fact that there's no fundamental plane equivalent for disks. Right. It's just. Well, yeah, right. It's Ajon, so it doesn't. So if I plot for the elliptical luminosity versus velocity dispersion, the scatter is correlated with size. If I plot rotation velocity versus luminosity for this galaxy, which is the Tully-Fisher relation, its scatter is not correlated with size.
We've heard about prolate galaxies quite a bit, especially at the higher redshifts, but I don't hear a whole lot about what might be signatures of prolate. For example, I would think that kinematics would be very valuable, but it'd be helpful if someone said, if you can get velocity dispersions down to, say, even 40, 50 kilometers, and you can get down to this mass, it'd be very helpful for us observers to, not me, but the young folks, to go out there and check out what fraction galaxies have the signatures that separate between, let's say, prolate galaxies to those that are disk-like, that are more edge-on. So if some theorist can say, yes, I've studied this, that'd be great. I'm sort of curious. I'm curious in general about the answers. I'm hoping it's also inspiration for the young folks to go out there and really track down these prolate systems that are supposedly 30%, which is not insignificant. That's not even a category up there, right? We're talking about disk and spheroids, but it's not in the prolate category.
Theorists want to comment on prolate galaxies and fractions of them.
So what we found in the Severino-Premack Deco 2015 paper, where we tried to explain the observations that were then coming in from the Candles survey. So first of all, the fraction of prolate galaxies at mass 10 to the 9.5 and below the fraction at redshift 1 and above is more than 50%. It's not 30%, observationally. No, but and at redshift 1.5 and above, the same is true up to a mass of 10 to the 10. So that is a clear majority. And this was confirmed by the Panja et al. James Webb Space Telescope paper, Panja, Hao, and Zhang et al. So it's a real phenomenon. What we found, as far as explaining it, is that these galaxies that are quite prolate are dark matter dominated often all the way to the core. They do not have a massive central bulge or anything like that. And as soon as you have a compaction event, okay, so let me suggest that you look at Polepich et al. 2019, the first paper on the properties of the galaxies in TNG 50. So there they have a nice set of plots where they've separated the gas and the stars. Their stars tend not to be as prolate as the observation suggests, but they are finding a certain fraction of prolate galaxies. But what was interesting is that they saw the same thing that we saw in our Vela simulations, namely that the gas is always a rotating disk. The gas is never prolate. So, and so you can see this in TNG 50 and probably also in other simulations, including Firebox, where you have all the gas data. So, and there's a complicated combination of how the gas is rotating compared to the orientation of the prolate stars. So the simulations show that. It's definitely something for the observers to look at. You have to simultaneously see the long axis of the prolate stars and then see how that relates to the rotation velocity of the gas.
Okay, observers, something to go and get data on. Now, last question, dwarf and satellite galaxy formation evolution. Who discussed that one? I'm sure there were people here discussing that one. Way at the back.
Okay, I'll bite on the what is the definition of a galaxy question. You got me. So I'm actually, honestly, I'm getting increasingly confused about the answer to this question. So operationally, at least in the local, in the near field, our working definition has really been like Willman and Strader, galaxy defined, as long as the dynamics of the system are, require a dark matter halo currently, then we call it a galaxy, and otherwise we call it a star cluster. But now I think, like, both from simulations and observations, like, it's getting quite blurry. So observationally, we've discovered lots of systems that have structural properties kind of right in between the globular clusters and ultrafaints, and their velocity dispersions are not well resolved one way or the other. And then in simulations, particularly this year and last year, people are starting to find systems that also fall in that regime. So maybe, for example, in the recent EDGE simulations, there are systems that form in a dark matter halo, but it's like a single starburst, and eventually the halo is mostly stripped away, so that when you look at the system today, there's no way to tell, at least from the simulation, that it ever formed in a halo, right? So should the working definition be that the stars once formed in a halo? And if that's the case, how can we tell? So I don't know. Those are some questions I have. I think the answer does, like, critically matter, because the number of these systems that formed in halos is really telling us about cosmology and dark matter. So we need to be able to disentangle that information somehow.
Anyone want to comment on that? Anybody got other ideas of an operative definition of a galaxy? Wait a minute.
So Kate and I were discussing this question a little bit, and one of the questions was, does it have to have a black hole at the center, for example? And our sort of working definition of a galaxy was that it formed by collapse within a dark matter halo, since, we're paying homage to the Blumenthal et al. Paper, I guess. But, and you can probably come up with a couple of corner cases that don't, like tidal dwarfs or something like that, but I'm just going to leave those out as exceptions, right? So then there's the question of, like, that distinguishes, say, dwarf galaxies from globular clusters in that one of them is dark matter dominated and the other one isn't. But there may be observational exceptions where you can no longer tell. I don't know if any of these have been, observationally demonstrated. But, maybe we should take it formed within a dark matter halo as good enough for now.
So just to be clear, by that definition, a tidal dwarf isn't a galaxy. It's some sort of superstar cluster. No, but I think this question is being motivated by edge cases, though. That's kind of the point, right?
I want a T-shirt that says "Galaxies are weird."
I was going to say that back in the old days, I thought that when we talked about AGNs, we had supermassive black holes, but they were still less than a tiny fraction of a galaxy's mass in terms of stars and stuff like that. So now we have these LRDs, which some people are proposing are almost close to a naked black hole, and yet I think most of us would still say that belongs closer to a galaxy class rather than a cluster class. So unless you want another category where you have black holes actually dominating, or it's really much bigger than what our local galaxies like, we may have to expand at least that part of the definition of a galaxy. Side comment historically.
I was just going to say, on the galaxy definition, another one that's been used a lot that I think still works reasonably well in a lot of cases, although I think it might get pushed on by the sort of ultra faints that people are starting to discover, is really, do you form all your stars in a single episode versus an extended star formation history? Because even the, uniformly ancient ultra faints still show in their enrichment patterns a clear extended star formation history, whereas, and yeah, there's there's the light element enrichment in the globulars, but that's very specific to very certain species. Like they don't have an iron spread, for example. So I think that still works pretty well in most every case, and would separate sort of, it's another physical line, and I think it's strongly correlated with things like, did it form in its own dark matter halo, but it's useful. I'd also just very briefly to David's point on the LRDs, this point got brought up a lot about them deviating from the stellar mass the stellar mass black hole mass relation. One, as several people brought up, that's still very uncertain because both the stellar masses and the black hole masses are very uncertain, and there are models where, yeah, it's slightly high, but it's maybe only a factor of a few higher on M black hole M star than today. It's also, in all these models where they're embedded in a star cluster, when you look at those models, it's very plausible that they're actually perfectly on M sigma, and it's just that, because if you take 10 to the 8th solar mass star cluster inside of 100 parsecs, sigma is 200 kilometers a second, so it should have a 10 to the 8th solar mass black hole. So again, I think these are important questions to figure out, to sort out. Can we measure eventually a velocity dispersion if they are in a star cluster, or really nail that down? But it's not clear, that they're really that overmassive, or which track they're evolving on, or even which of those is the more important relation for thinking about feedback and growth.
Okay. Any other questions from here that people were discussing? For example, what have we learned or are likely to learn measuring faint galaxies in different regimes beyond the Milky Way or M31? Are we on the cusp of a revolution in our understanding of dwarf galaxies and globular clusters, given all the data that's going to be coming online, or not?
Yeah, it's kind of related to the last point here, and I think Sebastian
ended the session by making us think about merger histories. So it's been, I think there's a growing consensus now in the Milky Way community that the Milky Way is kind of weird, formed pretty early for a galaxy of its mass. And I'm going to pose a question, which is, what do we think are interesting things to look at in terms of how the early formation history of the Milky Way might affect its satellite population, especially now that we have a growing sample of galaxies from Saga, from elves, in other parts of the nearby universe. And should the early formation history of the Milky Way have an effect? Should it not? And how do we test those questions? This seems like the kind of thing that you would want to test more in theory, because you can't really observe the merger histories of external galaxies.
Yep, there's a question for the back.
I was just going to comment that we actually see this reflected in the Saga data. So the Milky Way has the LMC and SMC, which makes it kind of an outlier. It has more bright satellites than most of the Saga hosts. But then in terms of the total satellite count, it's actually fluctuating downward compared to the rest of the Saga hosts. So that's like very much in line with the picture where the Milky Way is an old system that recently had the LMC and SMC added to it. So I think by doing, playing games like what is the total satellite population, what are the star formation histories of those satellites, you can basically infer the merger history from that, at least to some extent.
Okay, and
And also related to this, so the quenched fraction of satellites, it's another thing that can so the fact that Milky Way is an outlier is that most of its satellites are quenched, can also be an effect of disk being there for long enough time to dynamically quench them.
And I'll just add, I think there may be an interesting question that unites this and this, which is, now that observationally we're getting nice populations of satellites around nearby Milky Way and LMC analogs, if we can observe the host galaxies well enough, if we can look at things like metallicity gradients, morphology, dynamics, can we actually have priors on how they formed when they assembled? Maybe stellar halos might be tricky, although it's an interesting question too, so that we could unite these questions, at least in the relatively nearby universe. No. You think not? Okay, Frank's skeptical. No. Too much stochastic, okay.
Okay, it looks like we are done with our discussion session, and we'll let you go to your free afternoon. Thank you, everyone.
Thanks.
Just a reminder for anybody who has a poster outside,